Consider the initial value problem y prime is equals to lambda y subject to the initial condition y naught is equals to 1, where lambda is a real number or a complex number. I am going to find the region of absolute stability of the second order Runge Kutta method. So we are given that initial value problem there. For the region of absolute stability, we denote it by a gamma. It is the set of values of mu such that the absolute value of f of mu is less than 1. So when you are looking at that region of absolute stability, we need to write the iterations of the numerical method in the form yn plus 1 is equals to f of h lambda multiplied by yn. For the second order Runge Kutta method, we have k1 is equals to h multiplied by f of yn tn, and the k2 is equals to h of f of yn plus k1 plus tn plus 1. Then for our yn plus 1, we will get it as yn plus a half multiplied by k1 plus k2. So that's how we obtain the iterations there for the second order Runge Kutta method. And for our f there, we get it from what is on the right hand side here of our equation. So f of yn tn is equals to lambda yn. So using this f, we can then obtain our k1. We are saying k1 is h multiplied by f of yn tn. So k1 will be equals to h multiplied by lambda yn, just because we said that our f is lambda yn. Then for our k2 now, for our k2, wherever we are having yn, we are replacing with yn plus k1. So that would have k2 is equals to h multiplied by f of yn plus k1 tn plus 1. And when we substitute wherever we have n and we put yn plus k1 into this formula here, what we have there is h multiplied by lambda multiplied by yn plus k1. But we have the value of k1 here is h lambda yn, and that will give us h multiplied by lambda yn plus h multiplied by lambda yn. I can multiply throughout by the h lambda there, so that would have h lambda yn plus h squared lambda squared yn. So that's the expression that we have there for k2. So since we now have our k1 and k2, we now substitute it in this formula here, so that would have yn plus 1 is equals to yn plus half multiplied by h lambda yn plus h multiplied by lambda yn plus h squared lambda squared multiplied by yn. But here we have these two terms here, they are common, so we can add them so that they become a 2, so that our expression becomes yn plus a half multiplied by 2 multiplied by h lambda yn, then plus h squared lambda squared yn. Then multiply throughout by this half, then we'd have yn plus h multiplied by lambda yn plus h squared over 2 multiplied by lambda squared yn. Then we see that yn is common in this expression. We can factor it out. So we'd have yn plus 1 is equals to 1 plus h multiplied by lambda plus h squared lambda squared divided by 2, then multiplied by yn. So that's the yn plus 1 that we are having. Then compare it with this one that we have. Then by comparison, we see that f of h lambda is equals to 1 plus h lambda plus h squared lambda squared divided by 2. But this h lambda, we can write it as a different variable. We can assign the h lambda to the variable mu there. So when we replace wherever we're having h lambda, we put mu, we'll be having f of mu is equals to 1 plus mu squared divided by 2. But here we are saying for the region of absolute stability, we need that absolute value of f of mu to be less than 1. So we will have the absolute value of 1 plus mu squared divided by 2 is less than 1. But when we are having an absolute value, if you still recall, it will be saying that that value is less than 1 or greater than minus 1. So we can write that absolute value as an inequality. So we'll be having minus 1 is greater than 1 plus mu squared over 2, then less than 1. So that's the inequality that we are having. I can multiply that inequality there by a 2 throughout, so that we get rid of a 2 in the denominator there. So when you multiply the inequality by 2, we would get, and then I can subtract 2 from either sides of the inequality at less than 0. Then from this inequality, what you obtain there is two inequalities. Either we're having minus 4 is less than 2 mu plus mu squared, or 2 mu plus mu squared is less than 0. But looking at this inequality here, I can just put the minus 4 on the right hand side, so that would have 2 mu plus mu squared plus 4 is greater than 0. What we see here is this inequality is true for all values of mu. We are having a term which is squared there, and it's being added by a 4. So it will always be greater than 0. So this inequality is valid for all values of mu. But looking at this inequality, I can just factor on the mu there, so that would have mu then multiplied by 2 plus mu, then it's less than 0. So that's the inequality we now need to look at. So for this inequality, first you recall when we were solving inequalities, you need the critical values. So for the critical values, we look at the equation mu multiplied by 2 plus mu equals to 0. So the critical values there are mu equals to 0, or whatever 2 plus mu equals to 0, which will give us mu equals to minus 2. So I can just put a number line, then indicate my critical values. We have a 0, and the other critical value, we have a minus 2. Then we go on and analyze those three regions that we have there. So for the first region there, we are saying mu less than minus 2, this one going there. So what we look at, so we try to look at for a number which is in that region less than minus 2. You can take minus 3, so that if you substitute it here, we would have minus 3 multiplied by 2 minus 3, which gives us a 3. So we are saying it's positive. So we are saying in this region it's positive. Then we look at this region now between minus 2 and 0. We can look for a number between minus 2 and 0. I can take a minus 1. So if you substitute minus 1 here, we would have minus 1 then multiplied by 2 minus 1, which gives us a minus 1. So we are saying in that region there is negative. Then we look at this region now here going to infinity. We can take any number. We can take a 1. So we substitute it here, so that we have 1 multiplied by 2 minus 1, which gives us a 1. So we are saying in that region it will be positive. But what you are saying here is it's less than 0. So the correct answer is this one, where we have a negative. So the solution that we are having for that inequality there is mu is between minus 2 and 0 here. We can write that as an interval minus 2 to 0. So the region of absolute stability for the second order Runge Kutta method for the particular problem is minus 2 to 0.